Hello, welcome back. In this video, we'll discuss the free electron theory. There are two different free electron theories. The first theory is the classical free electron theory. This theory was proposed by Drude and Lorentz in 1900. The classical free electron theory failed to explain some of the experimental observations. Therefore, in 1928, Sommerfeld proposed the quantum free electron theory. The classical free electron theory is based on the following postulates. Postulates of classical free electron theory. The first postulate is, in an atom, electrons revolve around the nucleus and a metal is composed of such atoms. In an atom, electrons revolve around the nucleus and a metal is composed of such atoms. The second postulate is, the valence electrons of atoms are free to move about the whole volume of the metal, like the molecules of a perfect gas in a container. The collection of valence electrons from all the atoms in a given piece of metal forms free electron gas. The valence electrons of atoms are free to move about the whole volume of the metal, like the molecules of a perfect gas in a container. The collection of valence electrons from all the atoms in a given piece of metal forms electron gas. Since it is an electron gas, the electrons are free to move throughout the entire volume of the metal piece. The first postulate is, in an atom, electrons revolve around the nucleus and a metal is composed of such atoms. The second postulate introduces the concept of free electron gas. How the electron gas is created? The electron gas is created by the valence electrons. So a large number of valence electrons are released into the piece of metal, and the metal ion cores are placed at fixed locations at the lattice points in the piece of metal. The ion cores may be considered as they are suspended in a sea of electrons. Here we are comparing the electron gas with the perfect gas. In the case of a gas, the electrons are free to move randomly in the entire volume of the container. Similarly, here also we will have the electrons moving randomly all across the volume of the metal piece. The third postulate is, the free electrons move in random directions and collide with either positive ions fixed to the lattice or other free electrons. All the collisions are elastic in nature, hence there is no loss of energy. These free electrons move in random directions and collide with either positive ions fixed to the lattice or other free electrons. All the collisions are elastic or there is no loss of energy. The next postulate is, the movement of free electrons obey the laws of classical kinetic theory of gases. The movements of free electrons obey the laws of classical kinetic theory of gases. The fifth postulate is, the electron velocities, they obey the classical Maxwell-Boltzmann distribution. The electron velocities in a metal obey the classical Maxwell-Boltzmann distribution. The velocities of the electrons can be expressed using a statistical distribution. The statistical distribution that holds good in this case is the Maxwell-Boltzmann distribution. The next postulate is, the free electrons move in a completely uniform potential field due to the ions fixed in the lattice. The free electrons move in a completely uniform potential due to the ions fixed in the lattice. The last postulate is, when an electric field is applied to the metal, the free electrons are accelerated in the direction opposite to the direction of the applied electric field. When an electric field is applied to the metal, the free electrons are accelerated in a direction opposite to the direction of applied electric field. This is quite obvious because an electron that is placed in an external electric field experiences a force due to which there will be an acceleration. The classical free electron theory is successful in explaining some of the experimental results. We shall discuss the success of classical free electron theory. The classical free electron theory is successful in explaining the Ohm's law. It verifies the Ohm's law. The classical free electron theory successfully explains the electrical and thermal conductivity in metals. It explains the electrical and thermal conductivities in metals. the classical free electron theory successfully explains the relation between the electrical conductivity and the thermal conductivity, which is known as Wiedemann-French law. It verifies the Wiedemann-French law. Similarly, this theory also explains the optical properties of the metals. Now we shall see the drawbacks of classical free electron theory. The first drawback is it fails to explain the photoelectric effect, the Compton effect, and the blackbody radiation. It fails to explain the photoelectric effect, the Compton effect, and the blackbody radiation. According to this theory, the value for the specific heat of metals is given by 4.5 Ru, whereas the experimental value is nearly 3 Ru. Similarly, the value of the electronic specific heat is equal to 3/2 Ru, while the observed value is 0.01 Ru. So this is a deviation from the observations. According to this theory, the value of specific heat of metals is given by 4.5 Ru, where Ru is the universal gas constant. Experimentally, it was found that the value is 3 Ru. Similarly, the electronic specific heat, according to this theory, is 3/2 Ru, while the experimental result is 0.01 Ru. The third drawback is the electrical conductivity of semiconductors or insulators could not be explained using this model. Electrical conductivity of semiconductors or insulators could not be explained. Although this theory verifies the Wiedemann-French law, it fails to explain the Wiedemann-French law dependency in the low temperature region. It fails to explain Wiedemann-French law at low temperatures. The next drawback is this theory fails to explain the ferromagnetism and the paramagnetic susceptibility. It fails to explain the ferromagnetism and the paramagnetic susceptibility. Some of these drawbacks could be explained using the quantum free electron theory. Now we shall look at the postulates of the quantum free electron theory. Quantum free electron theory. This theory was proposed by Sommerfeld in 1928. In addition to the postulates of classical free electron theory, this theory adds two principles from the quantum mechanics, namely the Pauli's exclusion principle and the Fermi-Dirac statistics. This theory is an advancement of classical free electron theory. It uses two principles of quantum mechanics, namely the Pauli exclusion principle. Secondly, it applies the Fermi-Dirac statistics. These are the two concepts of quantum mechanics that are used to upgrade the classical free electron theory. The main assumptions are the eigenvalues of conduction electrons are quantized and are realized in terms of a set of energy levels. It introduces the concept of discrete energy levels, and the first assumption is the eigenvalues of conduction electrons are quantized and are realized in terms of a set of energy levels. The distribution of electrons in various allowed energy levels takes place according to the Pauli's exclusion principle. The distribution of electrons in various allowed energy levels takes place according to Pauli's exclusion principle. The electrons move in a constant potential inside the metal and are confined within the piece of metal. The electrons move in a constant potential inside the metal and are confined to the piece of metal. The mutual attraction between electrons and lattice ions and the repulsion between the individual electrons may be ignored. The mutual attraction between electrons and lattice ions and the repulsion between individual electrons may be ignored. The quantum free electron theory successful in overcoming the most of the challenges faced by the classical free electron theory. However, this theory also has certain drawbacks. The drawbacks are drawbacks of quantum free electron theory. The quantum free electron theory fails to explain the distinction between conductors, insulators, and semiconductors. It fails to distinguish the conductors, semiconductors, and the insulators. It fails to explain the occurrence of positive Hall coefficients in case of some metals like zinc. It fails to explain positive Hall coefficient of some metals. Example is zinc. To overcome the shortcomings of the quantum free electron theory, the band theory of solids is proposed. In this video, we have started by stating that there are two different free electron theories. The first one is the classical free electron theory, which was proposed in 1900 by Drude and Lorentz, and again in 1928 the quantum free electron theory was proposed by Sommerfeld. We have seen the postulates of classical free electron theory. We have seen the success of classical free electron theory. We have seen the drawbacks of classical free electron theory. We have seen the quantum free electron theory postulates. We have seen the drawbacks of quantum free electron theory. Thank you.